All right, so now we're going to use stats models to run an ordinary least squares regression of closed price onto the square feet and the number of bathrooms. So now our Y is still going to be our closed price array, and X is going to be 2 columns. It's still going to be square feet total, so the total square feet, but it's also going to be the total number of bathrooms, so baths total. And we're going to attach regression summary to the report. So we'll start with that. Reg will be equal to stats models dot ordinary least squares. Our ndog is going to be Y. X, our exogenous, is going to be X, but we have to add a constant. You can't forget to do that. We're going to fit, and we'll print our regression summary. So here, this model is a little bit of a better fit than one of the previous ones. So now we have 2 explanatory variables. So we have 2 explanatory variables, and based on this regression, so the question is, based on this regression, if you increase the square footage of a home by 150 square feet and add a bathroom, how much would the expected closed price increase? So remember for this, so this is maybe a little bit of a tricky question. The specification of this regression is we have price I is equal to our beta 0 plus our beta 1 multiplied by the square feet of the ith home plus beta 2 multiplied by the number of bathrooms, sub I plus our error term. So we want to know if we increase, so let's say we increase the square feet by 150, and we increase the number of bathrooms by 1, how much does the price increase? So this would mean we have a new price and an old price. The new price new, minus the old price old. You subtract the 2. So we want to know how much did the price actually increase, or what our estimated price actually increase. Beta 0 minus beta 0 cancel out. I'll go ahead and write it all out. So we get square feet new plus beta 2 times bath new. So maybe if there were 3 bathrooms before, maybe now there's 4. This would be minus beta 0 minus beta 1 of the square feet old minus beta 2 in the bathroom. Remember, this is the expected value. So we want to know the expected value. So in the expected value of our error term is 0. So if we take the expected value of all of this, we just get 0. So just to kind of not to get too off topic, but whenever we do this, we're saying we want to know, the expected price given, we know the square foot, and we know bathroom. This would mean that the expected value, and you remember back from module 4 and probability, and we talked about expected values and moments. The expected value of a constant is just a constant, so this would just be beta 0 plus now beta 1 times square feet. We know the square feet, so we just plug it in. And then beta 2, you factor it out. Beta 2, the expected value of bath. We know the bath because it's conditional on the number of bathrooms, so we just plug it in. Plus the expected value of our error term. The expected value of our error term is 0, so that just goes away. So that is, so keep that in mind as we do what we're doing. So we want to know the difference. So our intercept cancels out, and we can factor in, we can say beta 1 multiplied by, so we can factor beta 1 out. This would give us square foot new minus square foot old plus beta 2. We can factor that out, and we get the number of bathrooms new minus the number of bathrooms old. And we already know what this is. This is the change in square feet, which is equal to 150. And this is the change in bathrooms, which is equal to 1. So you just plug all that in. So this means that our increase in price, our change in price, our change in price is going to be equal to beta 1 multiplied by the change in square feet, which is 150, plus beta 2, our estimate for beta 2 multiplied by the change in bathrooms, which is 1. And then you just solve. So to do this, I'm gonna, or to show it, I'm gonna go back to our notebook file. Let's actually calculate it. So we know our reg parameters, regression parameters. The constant doesn't matter. Let's get a 1. So our second element multiplied by 150 plus our third element. Remember, Python starts at 0. Multiplied by 1. And this gives us $40,790. So this would be the expected increase in closing price given the improvements. Then provide a brief explanation. One more thing to before we talk about the issues in regression analysis, we'll talk about one more thing and what multicollinearity actually does to our estimates. So if I include, let's add another explanatory variable. We'll do beds total. So we add the total amount of bedrooms. We run this and look at the regression results. We can see that the R squared did increase slightly, but it was at a cost. You can see that the coefficient for the number of bedrooms is negative. So this could be because square feet, baths, and beds all have a high correlation between each other. So this could be a problem of multicollinearity. You can see it down here. The condition number is large. This might indicate that there are strong multicollinearity or other numerical problems in our data. So you can see that this is a problem. This could be a problem. So this, if you were to use this regression to estimate price, this could give you a unrealistic results. Maybe it's overfit. Maybe it fits the data well, but this couldn't actually be used for estimates or for inference or for or investment decision making, because the regression results, they're not necessarily realistic. You're saying as you increase the number of bedrooms, it decreases the value of the home. That doesn't quite make sense, but this may not be linear either. So these are collinear, and that is as a problem. So you couldn't have the number of bedrooms included in this regression, given all of the other independent variables. So that's it for this video. In the next video, we'll talk about the issues in regression analysis and the Gauss-Markov assumptions. And this is in chapter 2, I believe, or in chapter 3 when we talked about regression analysis.